So, in criteria of good estimator, there are 4 characteristics for an estimator to be a good estimator. Those 4 are unbiasedness, consistency, efficiency, and sufficiency. We have already discussed criteria for unbiasedness. So that is an estimator Tn is called unbiased estimator of theta if at all expectation of t is equal to theta. So the next criteria for good estimator is consistency. Let us see what is the criteria for, or what are the conditions for an estimator to be consistent estimator. Let x1, x2, so on xn be a random sample, okay, from a population with parameter theta. Okay, then an estimator Tn is called consistent estimator. When do you call it as a consistent estimator of theta? Means you have the criteria. First one is nothing but expectation of Tn should be equal to theta, which is nothing but for unbiasedness also. E of Tn is equal to theta. In addition to this, it should also satisfy that variance of Tn should approach to 0 as and turns to infinity. Okay, so for under unbiasedness, an estimator is called unbiased estimator if E of Tn is equal to theta. But to say an estimator is a consistent estimator, it should satisfy, along with this condition, variance should also be should turn to 0 as n turns to infinity. So let us do 2 problems on this so that you will understand. First one, show that sample mean is, this is the question, sample mean is a consistent estimator of parameter lambda for a sample of size n drawn from p lambda distribution. Okay, so here you need to prove that sample mean is consistent estimator of lambda for a random sample drawn from Poisson distribution. In the previous problems also, and for unbiasedness also, I said to follow a pattern. What is the sample size here? It is a sample of size n and it is drawn from Poisson distribution. This is nothing but x follows p lambda. So it is a random sample from Poisson distribution with parameter lambda. Specify its mean and variance. Mean of Poisson distribution is lambda. I think variance is also the same, which is nothing but lambda. And we know that in Poisson distribution mean and variance are equal. E of x is equal to lambda, V of x is equal to lambda. Now what is x bar? X bar we indicate that for sample mean. What is the formula for sample mean? 1 by n sigma I is equal to 1 to n xi. Now what is our objective? To show that x bar is consistent estimator of lambda. Means when do you call an estimator as a consistent estimator? E of x bar should be equal to lambda, and V of x bar should turn to 0 as and turns to infinity. When do you call an estimator as a consistent estimator? When E of x is equal to lambda and V of x tends to 0. Now we already know that. Let us check the first one, E of x bar, which is equal to E of x 1 by n sigma xi, which is equal to 1 by n sigma E of xi. 1 by n. What is the mean of normal Poisson distribution? Which is nothing but lambda. So you will get n lambda by n, which is nothing but lambda. So the first condition is satisfied. Let us verify the second one. V of x bar. What is the formula for x bar? 1 by n sigma xi. I hope this is a constant. Whenever a constant is taken out of the expectation, it will be squared. 1 by n sigma variance of xi. What is the variance of Poisson distribution? It's nothing but lambda. So as this is independent of I, you will get n lambda by n square, which is nothing but lambda by n. Here variance of x bar you got as lambda by n. As n turns to infinity, here the condition is as n turns to infinity, variance should approach to 0. As n turns to infinity, I hope 1 by n approaches to 0. So variance of x bar turns to 0 as n turns to infinity. So here we have observed that E of x bar is equal to lambda and V of x bar is approaching to 0 as n turns to infinity. From these two conditions, we can conclude that sample mean is a consistent estimator of lambda. So let us do another problem also. Let x1, x2, so on, xm be a random sample from B and P. What do you mean by B and P? Binomial distribution with parameters n comma p. Show that x bar by n is consistent estimator of p. Here x1, x2, xm. Here x1, x2, xm is a random sample. What is the sample size here? M is the sample size. It is a random sample from binomial distribution with parameters n comma p. You need to show that x bar by n is a consistent estimator of p. So what is the criteria for consistency? Means E of Tn should be equal to theta. Here V of Tn should approach to 0. Now, so what is given here? x1, x2, xm. What is the random sample size then? M is a random sample from B and P population. Okay. Now, you need to prove that x bar by n is a consistent estimator of P. You need to show that x bar by n is a consistent estimator of P. Then that is you need to show expectation of x bar by n is equal to P and variance of x bar by n approaches to 0 as n turns to infinity. These two you need to show. Criteria is nothing but E of Tn should be equal to theta, V of Tn is equal to 0. In place of T you have x bar by n, in place of theta you have P. Now what is the formula for x bar? X bar here is sample mean. Sample mean is nothing but sum of the observations by number of observations. Here the sample size is m not n because n is one of the parameters, as we are using n for one of the parameter in binomial distribution. To avoid confusion between the parameter and sample size, here we are indicating the sample size with m. Try to understand, in binomial distribution one of the parameter is n. So to avoid the confusion between the parameter and sample size, we here m is the sample size. So you will get, instead of m you will get 1 by m xi. Okay. Now let us verify the first one, expectation of x bar by n. So I hope 1 by n is a constant which can be taken out of the expectation. So 1 by n. What is the formula for x bar? 1 by n sigma I is equal to 1 to m xi. Again this m can be taken out, 1 by mn. Sigma can also be taken out of the expectation, E of xi. So this is nothing but 1 by mn. What is the mean of binomial distribution? Mean of binomial distribution is np. Variance of binomial distribution is npq. You know these two. Mean of binomial distribution is np and variance is npq. So 1 by mn. Mean is nothing but npq. So I is equal to 1 to n np. As these two are independent of I, you will get m here. Okay, this is the usual one. 1 by m mnp. Okay, m and mn cancels, you will get p. So expectation of x bar by n is equal to p. First condition is satisfied. Let us verify the second one. Variance of x bar by n. So n can be taken out, 1 by n square, variance of x bar. As whenever a constant is taken out of variance, it will be squared. So 1 by n square. Variance of x bar is nothing but 1 by n. Sigma I is equal to 1 to m xi. It will be squared. You will get 1 by n square m square sigma variance of xi. This is 1 by n square m square. Sigma variance of xi is nothing but npq. Again the summation is from 1 to m. As entire term is independent of m, you will get 1 by n square m square. You will get m in addition to this mnpq. So 1 mn cancels. You will get pq by nm. You got variance of x bar by n. So you need to prove variance of x bar by n approaches to 0 as n turns to infinity. So you have denominator in n. So which is nothing but 1 by n. You know that 1 by n approaches to 0 as n turns to infinity. So entire variance of x bar by n is approaching to 0 as n turns to infinity. So expectation of x bar by n is equal to p. Variance of x bar by n is equal to 0. So we can say that x bar by n is a consistent estimator of p. Thank you.